Good afternoon. Thank you for inviting me to this conference. I apologize, I'm maybe the only English-speaking speaker. My French is not sufficient enough to present in French. Why was it decided to use solar power on a mission to Jupiter? I will first of all describe you the objectives of the European mission to Jupiter, which we managed to launch in April this year. Why would we want to go to Jupiter? Jupiter is, first of all, is a very exciting object. We want to understand it. We want to understand the Jupiter as a system. We want to explore it. We want to understand the Jupiter atmosphere. People know the stripes and the large eye on its southern hemisphere. We want to understand the Jovian magnetosphere, which is very, very significantly larger than the Earth's. And we want to understand the interaction and existence of the Jovian moons and the ring system around it. Jupiter has very small objects around it as well, and it has a very thin ring system similar to Saturn, but thinner. On top of that, we want to explore the availability of habitable areas there. By habitability, we of course do not mean life, but we mean the capability that life could exist in any of the Jupiter system and most likely on the moons. What do you need for life? As a precursor for habitability, you need essentially liquid water. You need the essential ingredients like carbon, hydrogen, nitrogen, oxygen, maybe phosphorus, maybe sulfur. You need chemical energy. You need to have energy available such that chemical reactions could take place. You need finally a stable environment, and by stable, obviously on geological timescales, like similar timescales which took life on Earth to spring. Such principal essentials could be available in Jupiter's moons, and therefore we want to go there and investigate particularly Ganymede, but also Europa, which has even active surfaces, and Callisto, and understand how these moons could potentially harbor life. How we do this? We launch a spacecraft, and this is a model of the Jupiter spacecraft which we launched. You can see, obviously, it is a big box containing all the necessary equipment, including propellant. Immediately you see the very high gain antenna. It's a parabolic antenna. The human is comparable in size here. It is 2.5 meters. And you can see immediately that we choose for solar power generated by solar arrays, which are very big, and I will come more to this in the rest of my presentation. Around this, you see with arrows indicated the scientific instruments. At the back here, several on an individual magnetometer boom and the radar subsurface antenna. The launch mass of this whole spacecraft was about 6 tons, of which less than half is the spacecraft and more than half is the propellant, which we need to take with us. We have a large solar array. We have a large memory, which allows us flexibility for storing scientific data. Because we have a low data rate, we only can transmit 2 gigabits per 24 hours. And we have a very far distance, which actually means that the round-trip signal for communications is up to 90 minutes. The scientific instruments, briefly covered, include a camera in the visible range, and hyperspectral imager in the near-infrared range. The wavelengths are given down here. A UV spectrometer imaging both above the moons and the Jovian atmosphere. A sub-millimeter wave instruments, a laser altimeter for measuring different shapes of the moons, and an ice-penetrating radar. And then for the more in situ and geophysical instruments, we have a magnetometer with a very fine resolution to measure liquid water, a particle package which, with a very wide range of plasma and neutral coverages, and the radio and plasma wave instrument measuring both the potential of the plasma but also electric and magnetic waves traveling in the Jovian plasma. Then we use the spacecraft itself as a test mass and measure the distance to the Earth, and by this we can map gravitational field, and by understanding this, the path, you can then understand the distribution of mass in a respective object. And this is the gravity and geophysics instrument. And then additionally, we measure with a ground-based instrument, which is using essentially differential interferometry of the telemetry signal, the angular position of the spacecraft, giving us more information on the trajectory the spacecraft is actually traveling. The challenges of such a program are, first of all, that it is a very large mission. I gave you an impression with the various set of instrumentation which we want to take, which by itself then also includes a very large team. We have 10 instruments, we have 10 consortia building these instruments, and of course we have the entire spacecraft manufactured throughout countries in Europe. And I think the team size is of the order of 250, 300 people who worked on this at any point in time on this. We have a long cruise. I will touch upon this as well. Jupiter is far, but it's also difficult to reach. We have a complex navigation in the Jupiter system, which requires some autonomy on the spacecraft. Then, most importantly, actually, we have a very intense radiation environment. The Jovian field has a very strong magnetic field, which manages to cover charged particles very well, and these are ionizing our electronics and by that damaging it. We have a power and thermal challenge. Jupiter is far away from the sun, it is pretty dark, and by that it is very cold. And we need to have the internal to the spacecraft, we need to be electromagnetic clean, because we're measuring plasma and magnetic waves to very low sensitivity. We have a broad science and a very low, reasonably low data rate. I mentioned before, this was one of the successes of ESA this year. On 14th of April, we managed to launch the spacecraft. It is now in a trajectory in the vicinity of the Earth, and actually, as we speak, within 1 hour, we will make our first big interplanetary trajectory correction maneuver, which will then bring it back on a trajectory back to the Earth in August next year for its first flyby, for its first gravity assist flyby. Here is a little bit shown in more detail. First of all, the trajectory. We have several flybys in order to have finally a trajectory which has sufficient eccentricity to match Jupiter orbit. As I mentioned before, we will have a flyby of the Earth in August next year. We will then have a Venus flyby, which actually brings us closest to the Sun. And then we will have two more Earth flybys where we finally expect to arrive in Jupiter in middle of 2023. And then we will have a phase orbiting Jupiter, flying by the 3 outer Galilean moons, Callisto, Ganymede, and Europa. And then we will basically inject ourselves into an orbit around Ganymede, and we will end the mission at Ganymede. What are the main principal requirements of a power system on a spacecraft? Well, obviously, there needs to be stable power for operating the spacecraft. You need the spacecraft computer, you need to have communications, and you need to have a proper stabilized bus, typically 24 volts. You need to power instrumentation. Scientific instrumentation can be switched on and off, so there might be a bit of variation in the power budget, and you can use the distribution of the load on the bus, you can use that to balance out the available power. And particularly for going to Jupiter, you need to consider heating. I mentioned before, Jupiter is far away. I will come to this more and more. And therefore, you need to have the capability to keep sensitive electronics on the outside, but also on the inside within an operating range. Here's a simple graph which actually illustrates nothing else than the 1/r squared law. It basically says the further we go away from the Earth, the lower power we get from the Sun. And here's the point of the Earth, where we have in Earth orbit, we have 1,360 watts per square meter. This is in space business a number to remember. And if we use this as unity, then we will see when we go to the closest approach, this, by the way, is not the Venus distance, but is the design distance, then we increase this by 2. And if we go out to Jupiter, then actually we're left with 1.3%, which is 45 watts per square meter equivalent then. If we were to extend this curve further out to Saturn, then this turns actually to 14 meters per watts per square meter. So that is actually also then another indication that it becomes very, very low, the power we have available. Here's another graph which shows similar information. It gives the distance of the trajectory of the JUICE spacecraft with respect to the Sun in pink and with respect to the Earth in blue. And you should be able to see these yellow triangles, which are actually the gravitational assists, which I said Earth, Venus, Earth, Earth. And you can see that we're actually staying quite a while within a comfortable distance to the Sun. Then we go further out before we finally go far out to Jupiter. This is nothing else than the trajectory I showed you before. So what are the elements? Obviously, if you look back to the distance to the Sun, you will notice 45 watts per square meter is challenging. So how do we support power? There are two basic possibilities. The classical one, actually on outer planets, is to rely on a multi-mission radioisotopic thermal generator, which has been developed by NASA, which has been used on the Ulysses spacecraft. It is actually mounted, I think you can see it out here. Yes, it's this black thing sticking out here. And it is being used on several Mars rovers. I just got one image from Curiosity here showing that you power this with these thermal generators. The power generators have advantages and disadvantages, of course. They are this is basically the shape they look like. You have in the internal, you have the plutonium filled cavity, which is because of radioactive decay generating heat. And outside you have the heat control system where the thermoelectric generator is located and where you finally generate the heat. There is, in addition to this, there is an inefficiency here, and you need to cool the entire unit, which is done out here with cooling fins. I have a few numbers here at the bottom. Basically, one of these units is about 45 kilograms. It produces, at beginning of life, 125 watts, and towards the end of the life, more like 100 watts. This is due to the degradation of the plutonium, the radioactive decay, but it's also due to the degeneration of the thermoelectric power converter. In order to generate sufficient power and in order to have just some redundancy, typically 6 modules are being used, whereby 5 is the design value and 1 is as a spare module. And I said before, on top of the electric power which you can generate with this, you typically also have a heat of 1680 watts, 1690 watts, which needs to be radiated to space in order to keep this thing cool. The other alternative is, of course, a solar cell. A solar cell, we used in our case a 3C28 from Azure, which has a shape of 8 by 4 centimeters. It's not very big, it's only this size. But it has a triple junction gallium arsenide layout. This is different than what is being standard used on the Earth. The standard solar cells which we see appearing on rooftops and in the countryside nowadays are mainly based on silicon. Silicon is much cheaper, silicon has lower efficiency, and silicon has higher degradation due to radiation. Gallium arsenide is rather robust to radiation, and if you put 3 different cells above each other, you actually manage to get a broader spectrum of the sun radiation with your efficiency curve. So actually, your total efficiency then is the sum of these 3 individual curves, which then can reach 33% at the beginning of life, and depending on the temperature and depending on the radiation degradation, actually we designed for 24% at end of life. In the meantime, there are bigger cells. As I said, Azure, we can be proud of. This is European development. These cells then get integrated into solar panels. We have 22,000 cells integrated in our solar panels. And here is the solar panels folded on the actual spacecraft, and one panel shown on the outside here. And of course, obviously, as you could see at the beginning, it is a very large solar surface. It is a panel which is being unfolded. It has a final shape is a cross shape, and it is first unfolded that the extended side is being unfolded, and afterward that with a self-locking mechanism and self-blocking mechanism, actually, the sideways panels are being unfolded. What you can see here in the picture is a test in the clean room of the deployment of one axis, of the long axis of the solar panel, and it basically, with comparisons with the human people, it gives you an impression of the size. And then in the following, also from a test, obviously we need to separately deploy the sideways panel, because in such a way that we can have a gravity relief. We cannot operate this in one case on the ground. Now, comparing the two technologies and making a trade-off should be answering the question why we did what we did. And there are 2 components. There is a technical component, and there is actually an important programmatic component to that. If we start at the beginning with the design, assuming the design we choose, as I said before, 5 RTGs, 5 radiothermal generators will produce roughly 500 watts. Using solar cells gives one the capability to design for larger numbers, for larger power availability, and we choose 800 watts. So it gives us more flexibility. The total mass of the solar array is higher. However, if you compare it to the watt per kilogram, actually the ratio for solar panels is better. So actually, the watt you can generate with the solar electric power at Jupiter is more efficient by using solar channels. You have a risk of failure. The risk of failure in the radiothermal generator is being mitigated by flying an additional mass, an additional unit to counteract. On the solar panel, on the other hand, you could lose a string, you could lose 2 strings, and then you basically increase your surface area to counteract this failure. And therefore, we designed for single string failure tolerant by increasing the area, by making the electronics in such a way that we can ignore 1 string. The size is more favorable for the solar generator, for the radioactive generator. it is about 60 by 60, 65 by 65 centimeters. So it is actually a bit more than half a meter in both dimensions. You use this 6 times, they can be stacked above each other, and they can be built fairly compact. They need to accommodate it on the outside of the spacecraft because of the heat power dissipated. And as you can immediately see, the large solar arrays which we deployed, they are large, and they're basically 84 square meters, which is almost 27 by 27 tip-to-tip in size. The performance the performance degradation is better also in the RTG. You lose about 1.6% per year, so per time, and so it's about similar. In the solar generator, you lose about the same amount as with the other. The accommodation I already mentioned, but the large size is giving quite an inertia to the spacecraft, so it will impact on the movability and on the control of your spacecraft. We circumvented it by having large reaction wheels, the largest we have in Europe, and we still maintain, which of course need more power, need more mass, and we still maintain a good control of the spacecraft. Coming to the programmatic comparison of these two technologies, first of all, there is a major item with radioactive generators. In Europe, we are not qualified on the entire launch and integration segment to handle radioactive hardware. We would have to upgrade all the integrations of the spacecraft, to the launcher, and all the handling on the launcher to be able to handle the safety issues which come along with radioactivity. On the solar panel, on the other hand, we are of course fully compliant. And then a final argument on the programmatic section is the European independence. Interestingly, plutonium is not being enriched anymore because it can be used for weapons, and therefore the civil production has been actually run down. And as far as I'm aware, the production of plutonium for these MMRTGs has not yet been restarted for the last 20-25 years in the US. So the availability of plutonium is becoming less. Therefore, also it will be over time increasingly difficult to obtain the number of generators, the plutonium for the generators which are needed. And I would not be surprised if NASA and the US would give priority to their own missions and not to European mission. Whereas on the other hand, with the solar cells, we're fully compliant, we're fully independent, and actually we have procured and managed solar cells which are now by our company being bought for a US mission to Jupiter as well. So in the end, I hope I convinced you and I explained to you why we did what we did. On top of it, we have the solar generation by solar cells, by 10 solar panels, 5 on each side of the spacecraft. We have 1 degree of freedom. We can orient the solar array in around 1 degree in order to maintain it exposed to the sun. We add an additional rechargeable battery, which has also the capability to adapt to peak power demands. So we are not even limited by the power by the solar panel, but we actually have additional power available from the battery. And we have a stable 28 volt on the power bus, which is actually driven, what you can see here, by a maximum power point tracker. This is basically the IV curve, the voltage versus power curve coming out of a solar panel, and this is the curve as a function of voltage of the power to be extracted from a solar cell. In conclusion, I gave you in the beginning, Jupiter is, with current technology, I should say, probably the outer limit what can be reached with solar cells, because then if you go further, the solar panels become very, very large, at least with current technology. Maybe in future we can increase that. The power generation by the solar arrays is simpler to manage than with the radiothermal generators, considering the heat production, the autonomy, and the radioactivity. The available end-of-life power is higher, and this is the design value of a spacecraft. And the drawbacks can be overcome with a spacecraft design, like I mentioned to you, particularly the inertia and the exposure to the sun with larger reaction wheels and with solar array drive mechanisms, respectively. And finally, ESA has deployed with European development and European autonomy, particularly led by Azure and a consortium led by Airbus in the Netherlands, the largest solar panels on a science mission, I must say, around the Earth. They are actually spacecraft, telecommunication spacecraft with even larger solar panels. And this concludes my presentation, and I thank you for your attention.
I will try my best in English. Thank you very much for your talk. It's maybe a much larger question, but how did the decision process was made to go to the solar array, solution for the JUICE mission? Because you said we can see that the power generation by solar array is simpler to manage, and the drawbacks can be overcome by spacecraft design. But if you didn't have the problem of finding the materials for the MMR TG, would you have went for the multi-mission radiotropic thermal power generation?
No. No, I think it is the combination of all the factors which are summarized here, which actually made us go there, and particularly the available power. At the very beginning of a mission, when you design a space mission, you want to have the possibility to grow, because you have good estimates, and very often these estimates are optimistic. And actually, the 800 we have here is what we need as a minimum. We would not have been able to build JUICE in the size it has with being constrained to 500 watts. And so so there are a couple of engineering decisions here as well, which are driving this.
You said that the plutonium production did not restart in the US, and you said that maybe in the next year there will be impacts on the ESA mission program. What will be do you have already a more precise idea on the consequences of this impact?
It may not only impact ESA, it may also impact NASA. It may impact the two spacefaring nation organizations which are going to the outer planet. On ESA side, I do not have the impact yet. On ESA side, we're looking into alternatives. We're looking into alternatives not as high in heat and radioactivity as plutonium, for instance, americium. We are investigating a mission to the outer planets Uranus and Neptune, but these are in a very, very early stage and are used as technology reference missions where we say, here is a goal. What if we want to use this? What are the technology steps we need? And one of them is obviously power, which we need to look into. So with this having in a study yet and not having a project limitation, at this point in time we do not have an impact, and the forecast is very, very difficult.
No other questions? So yes, I can summarize now the presentation, maybe in French.
Please.
Sorry. vous vous êtes demandé à l'origine de cette conférence, pourquoi a-t-on décidé d'utiliser l'énergie solaire pour cette mission vers Jupiter? Et donc cette conférence nous a emmenés presque aux confins du système solaire. Alors vous avez rappelé d'abord les objectifs scientifiques de cette mission qui consistent essentiellement à caractériser Jupiter, donc son atmosphère, sa magnétosphère, ses satellites, et puis aussi plus généralement peut-être étudier les mondes habitables avec 4 éléments essentiels: l'eau, des éléments chimiques, l'énergie chimique et un environnement stable. Et puis vous nous avez présenté l'engin, le spacecraft, qui s'appelle JUICE, avec ses différents détecteurs, caméra, laser, magnétomètre, interféromètre, donc un concentré véritablement de technologie. Et puis vous nous avez mentionné que cette incroyable mission est soumise à disons, des défis à la fois humains et techniques. Défis humains parce que c'est une grande mission qui implique de nombreuses équipes, mais aussi un véritable défi technique puisqu'il est d'abord difficile d'atteindre Jupiter, planète lointaine pour nous, et il est notamment difficile de faire face au flot de particules chargées qui peuvent notamment perturber l'électronique. Et vous nous avez montré que la trajectoire envisagée pour atteindre Jupiter va devoir faire plusieurs tours autour du Soleil avec une arrivée prévue assez tardivement à la mi-2030. Donc il y a des problèmes de trajectoire et puis bien sûr il y a des problèmes aussi d'énergie pour contrôler l'engin et ses instruments. Et alors là, vous nous avez présenté 2 solutions possibles. La première solution, donc, c'est le développement d'un générateur de puissance qui a déjà été implémenté, comme vous l'avez rappelé, dans des engins comme Curiosity. Et puis la deuxième solution, c'est l'alternative des cellules solaires, donc des gros panneaux solaires. En l'occurrence, 10 seront implémentés pour JUICE en forme de croix. Ce qui peut paraître assez ambitieux, puisque comme vous l'avez montré avec ce graphique, on a beaucoup moins d'énergie solaire à mesure qu'on se rapproche de Jupiter. On arrive à 3% de la puissance qu'on aurait à côté de la Terre. Mais en fait, en comparant les 2 techniques possibles, donc à la fois les cellules solaires et les générateurs de puissance, on se rend compte que les avantages sont bien supérieurs aux inconvénients pour les cellules solaires, notamment parce qu'en fait, elles apportent dans l'ensemble plus de puissance aussi par kilogramme. Qu'en prime, elles permettent aussi une protection contre les rayonnements externes. Donc voilà, quelques avantages parmi d'autres, même s'il y a quand même quelques inconvénients. Le fait notamment que les panneaux prennent beaucoup plus de place et qu'il y a aussi des enjeux de design de l'engin pour pouvoir implémenter ces panneaux. Et aussi le fait que, à cause notamment des particules chargées, ces panneaux peuvent influer sur l'orientation de l'engin et donc il faut aussi prendre cela en compte. Voilà, et donc vous avez conclu en disant que finalement, cette technique du solaire, même si elle arrive à ses limites quand on envisage des voyages aussi lointains, elle est quand même préférable dans le cas de JUICE. Et donc, je crois qu'il n'y a plus qu'à souhaiter bonne chance, good luck to JUICE dans son voyage. Merci beaucoup.
Merci beaucoup.